Hello everyone, it's me, Billy Younger again, and this time I'm going to teach you how to compute a curl. A curl is that del operator crossed with a vector field. So we're going to actually learn how to compute that. We already know we already know what the del operator is. We've computed a dot product with the del operator on a vector field. Now we're going to do the del operator performing a cross product on a vector field. So let's get started. Again, I should reiterate that this is only for Cartesian coordinates x, y, and z. There's a whole other process that you have to go through when you're actually trying to compute one for polar coordinates or cylindrical coordinates or spherical coordinates, any of that kind of stuff. Parabolic, hyperbolic, all those coordinates, elliptical. So, anyways, I hope to make some videos on that later, but right now I'm just showing you how to do the brute force method that we can make use of to understand Maxwell's equation. So let me turn on my document can and get started. So I'm reusing the paper that I did for the divergence. Again, we're going to start off with a vector field, and that vector field is basically just an assignment of a vector quantity, uh, A, the vector, for each point in space, x, y, z, and maybe it depends on t as well. So that really is what the vector field is. So like I said, it can be a function of x, y, and z. It can be all sorts of stuff. But the main thing is a vector assigned to each component or to each point in space x, y, and z. But x, y, and z may actually be explicit variables in the actual vector field. What I wish to calculate is del cross A, which is called the curl. Now, the curl is a measure of how much basically a vector field tends to go around in some sense, whether it has sort of flow lines, if you will, around a particular point, whereas the divergence was whether it has like radial lines leaving or entering a particular point or points. So let us calculate this one. We know what our cross product means. I've showed you how to use a determinant for that. We know what the del operator is, and in fact, I'm going to reiterate that a short version of writing this is to write I hat partial with respect to x. So in other words, just the partial derivative with respect to x, but I'm just writing it partial symbol sub x, so that I don't have to write a fraction bar and then another partial symbol and then an x. It would also be j partial sub y, and finally, I'm sorry I wrote it up high. I forgot I was going to write it in the simplified form, partial with respect to z. So that'll save us a little trouble. So if I want to calculate the actual curl of A, what I'm going to do is take the determinant of the matrix formed by an I hat, a j hat, and a k hat in the first row, a partial with respect to x, partial with respect to y, partial with respect to z in the second row, and then a sub x, the x component of that a vector that we talked about earlier, that vector field, plus a sub y, and then a sub z. Again, each of these are functions of x, y, and z. Using my rule that I did before, which is basically I'll expand upon the I. The I has an exponent of forces -1 have an exponent of 1 plus 1, so that's going to be positive, which means I can cover up this column and this row, and then just do that minus that. So I'm going to say I hat partial with respect to x of a sub y, or excuse me, partial with respect to y. Sorry about that. Partial with respect to y of a sub z minus partial with respect to z of a sub y plus j hat. Now this one's covered up and this one's covered up, but to make up for the -1 to the 3 power, I'm going to do it in the opposite order. So I'll say partial with respect to z of a sub x minus partial with respect to x of a sub z. And then the third part would be k hat, covering up this column and this row. What's left is this minus this, so it's a partial with respect to x of a sub y minus the partial with respect to y of a sub x. Or writing it in its full gory details, it would be uh, partial of a sub z with respect to y minus partial of a sub y with respect to z I hat plus partial of a sub x with respect to z minus the partial of a sub z with respect to x j hat plus partial of a sub y with respect to x minus partial of a sub x with respect to y k hat. So that's it. That's the gory formula for the cross product of del operator with the vector field A, and it's also called the curl of A. Again, this does not work in the x, y, and it only works in the x, y, z coordinate system in Cartesian coordinates. If you wanted to use other coordinate systems, spherical, cylindrical, parabolic, or elliptical, hyperbolic, any of those, then you're going to have to uh, pay the piper and basically apply the chain rule over and over. So hopefully I'll do a video on that later. I think this is enough to get you started on making use of them and understanding Maxwell's equations. That's it. Have a good day.